If all natural gas came out of the ground in pure form, we wouldn't need this glycol dehydration unit. But almost all natural gas streams leaving the reservoir contain water vapor, and some even contain free water. As natural gas travels up the wellbore to the surface, it cools due to pressure reduction and conduction of heat to formation walls. When it reaches the surface, the natural gas is usually saturated with water vapor, and additional cooling causes free water to form. Further gas cooling causes hydrates to form. Hydrates cause serious equipment damage and flow restrictions. For successful gas processing, the water must be separated from the natural gas. But how is this done? Well, there are several methods for dehydrating natural gas. However, in this program, we'll examine the operation of a glycol dehydration unit using triethylene glycol. After the gas and water are separated, the glycol and water must be separated so that the glycol can be reused. The glycol dehydration unit performs a vital function in today's natural gas processing. Prior to viewing this program, you should have successfully completed the modules entitled Principles of Glycol Dehydration and Basic Principles of Pressure and Temperature. Now, if you haven't, please stop this tape and study these programs before proceeding. This is the first section of a three-section module on the operation of a glycol dehydration unit. In the first section, we'll look at liquid desiccants, the importance of dew point temperature and dew point depression, and process variables which affect glycol dehydration. To briefly review what you've already learned, glycol dehydration is an absorption process where lean glycol absorbs water from wet natural gas in the contactor column. Next, the water is removed from the glycol through the distillation process in the regenerator. Then the glycol is reused. Let's also review two important principles of temperature and pressure. At constant pressure, the water content of gas increases as the gas temperature increases. At constant temperature, the water content of gas increases as the gas pressure decreases. So, let's start with desiccants. A substance that removes water from another substance when the two are brought together is called a desiccant. Glycol is the liquid desiccant in the glycol dehydration process, removing water from natural gas. Now, there are many types of liquid desiccants used in gas processing. However, in this program, we will only discuss triethylene glycol, or TEG. Now, TEG is preferred in dehydration units because it is easily regenerated due to its high boiling point and other physical properties. It has a high decomposition temperature of 404 degrees Fahrenheit. It has lower vaporization losses than other glycols, and it has lower capital and operating costs than other glycol systems. To describe a dehydration unit's performance, you can monitor the dew point temperature and dew point depression. Now, dew point temperature, or simply dew point, is the temperature at which natural gas is saturated with water vapor at any given pressure. When gas is above its dew point, the gas can absorb water. When the gas is below its dew point, water will condense out of the gas. Since natural gas is considered saturated when it leaves the wellhead, the gas is said to be at its dew point temperature. Dew point depression describes how much water vapor has been removed from the natural gas. It is the difference between the dew point temperature of the inlet gas and the dew point temperature of the outlet gas following dehydration. Now, the actual temperature of the inlet and outlet gas does not change. For example, If the inlet gas temperature to the contactor is 100 degrees Fahrenheit and it has a dew point temperature of 100 degrees Fahrenheit, and the outlet gas temperature from the contactor is 100 degrees Fahrenheit and it has a dew point temperature of 35 degrees Fahrenheit, then the dew point depression is 100 degrees Fahrenheit minus 35 degrees Fahrenheit, which equals 65 degrees Fahrenheit. The goal in operation is to achieve the dew point depression that meets contract specifications for the water content in gas. Now, several process variables determine the degree of water removal in any glycol dehydration unit. The variables which affect the unit's efficiency are inlet gas temperature, inlet gas pressure, gas flow rate, inlet glycol temperature, glycol concentration, and glycol circulation rate. The temperature of the incoming gas has a significant effect on the water content of the gas entering the contactor. Remember, at constant pressure, the water content of the inlet gas increases as the gas temperature is increased. The more water vapor that the gas contains, the more water must be removed by the unit to reach the desired water content of the outlet gas. For example, at 1000 psig inlet pressure, changing the gas temperature from 100 degrees Fahrenheit to 120 degrees Fahrenheit will double the amount of water vapor that will be carried by the saturated gas. The inlet gas temperature range for successful glycol dehydration is between 60 degrees Fahrenheit up to 100 degrees Fahrenheit. Inlet gas temperatures above 130 degrees Fahrenheit make normal glycol dehydration almost impossible. In cold weather, line heaters heat the gas stream ahead of the dehydration unit to maintain a minimum inlet gas temperature of 50 degrees Fahrenheit. Minimum inlet gas temperature is set by the viscosity of the glycol being used. Depending on the composition and pressure of the gas, hydrates may form at temperatures well above 50 degrees Fahrenheit. Therefore, a higher inlet gas temperature is required to avoid plugging problems from hydrates. Now, low inlet gas temperatures increase the tendency of glycol foaming. As you will see later, foaming creates significant operating problems. Now, in the normal operating range of a glycol dehydration unit, inlet gas pressure is not a critical factor. However, at constant temperature, gas can hold more water as the pressure is reduced. Therefore, operating the unit with a higher inlet gas pressure will lower the water content of the gas. For a unit to operate efficiently, the gas flow rate must be maintained in a specific range. Now, if the flow rate falls outside these limits, either higher or lower, problems can develop. Falling below the specified flow rate causes a loss in efficiency and may increase the outlet gas dew point, depending on the design of the trays or packing in the contactor column. If the flow rate rises above the specified range, reboiler overload occurs. When the reboiler is overloaded, insufficient glycol regeneration and increased outlet gas dew point result. The amount of glycol carried out with the dry gas also increases. If the gas flow rate is high enough, all the glycol can be carried out of the contactor at one time. A smooth flow rate without rapid surges or changes prevents a loss of seal in the contactor downcomers. Seal loss allows gas to bypass the trays and causes high outlet gas dew points and high glycol loss with the outlet gas. A glycol inlet temperature of 10 degrees to 15 degrees Fahrenheit higher than the inlet gas temperature prevents hydrocarbon condensation in the glycol. Hydrocarbon condensation increases foaming, increases carbon buildup on the reboiler fire tube, and reduces carbon filter life. The process variable with the greatest effect on dew point depression is the degree of glycol reconcentration, also known as glycol purity. Higher dew point depressions can be obtained with higher glycol concentrations. However, Stripping gas must be used to achieve these levels of glycol purity. Stripping gas is natural gas percolated through glycol, being regenerated to help remove the water that cannot be removed by the distillation process. In some systems, the gas is percolated through the glycol inside the reboiler. In other systems, there is a stripping column located between the reboiler and the surge tank. If the glycol circulation rate is increased without changing other variables, the outlet dew point will be decreased. However, to produce the desired outlet gas dew point, you should use the lowest glycol circulation rate possible, because an excessive glycol circulation rate can cause the following problems: an increase in fuel consumption, an exceeded reboiler capacity, an increased overhead glycol loss due to the higher temperature of lean glycol going to the contactor, and an increase in pump maintenance. And that wraps up this section. In it, we discussed the importance of dew points and dew point depression, and saw how variables in the process affect the efficiency of the glycol dehydration system. Take some time now to read over this section in your student manual. Review this videotape if needed. Then when you're ready, answer the questions at the end of this section. Now in the next section, we'll look at the operation and controls of a glycol dehydration unit in detail. See you shortly. Well, I think you have a good idea of the process variables for glycol dehydration. Now in this section, we'll see how to operate the glycol dehydration system and how to control the process. This is the second section of a 3-section module on glycol dehydration unit operation. In this section, we'll look at the individual components that make up the glycol dehydration unit. We'll also see how the components are all related to one another in the overall system. Better dehydration results and significant savings are achieved when dehydration systems are operated properly. Efficiently operating a glycol dehydration system requires a good understanding of the dehydration process variables, and dew points. You must also understand the operation of individual components within the system. Let's start with the inlet separator. Now the inlet gas stream first enters the dehydration unit through an inlet gas separator. Here, free liquids in the gas stream are removed. Wet gas leaves the separator through a mist eliminator, which eliminates almost all carryover of free liquids to the contactor column. The inlet separator should be checked regularly. Overloading the inlet separator causes excessive liquid carryover into the contactor column, which causes foaming. Therefore, for proper operation, it is important to routinely monitor liquid levels and their controls. The function of the contactor column, also called an absorber, is to remove water vapor from natural gas by physically bringing together the upflowing natural gas with the downflowing glycol solution. The glycol absorbs the water vapor from the natural gas. Contactor columns are designed to accommodate a certain gas volume and pressure. If these design specifications are exceeded, then glycol losses and outlet gas dew point will increase. Contactor columns usually contain either tray, random packing, or structured packing. Now for a large volume of gas, the contactor is usually a tray column consisting of 4 to 12 trays. And of course, the greater the number of trays, the more moisture can be removed. Each tray has openings with bubble caps bolted over them. The upflowing gas is forced through these caps and bubbles evenly through the downflowing glycol. The gas gives up water, and becomes drier as it passes upward through each succeeding tray. The glycol becomes more saturated with water as it flows downward over each tray. Weirs, which are dam-like devices, maintain the level of glycol above the slots in the bubble caps. The downcomers carry the glycol to the trays below. In smaller capacity units, contactors having a diameter of 18 inches or less, random packing may be used instead of trays. This packing is metal, like these, or it could be plastic or ceramic structures. These structures provide a large surface area for the glycol solution to spread out and make better contact with the gas. Random packing is poured into the contactor onto a support grid. 4 feet of packing is usually standard and sufficient to achieve the dew point depressions up to 55 to 65 degrees Fahrenheit. If higher dew point depressions are needed, additional packing may be required. Packed columns utilize the same process as tray columns, where liquid glycol flows down over the packing and the gas flows up through the packing. Packed columns are less expensive. However, they tend to channel and have poor flow distribution. Channeling is when the liquid glycol flows in streams throughout the random packing. Channeling limits the surface area where the glycol and gas come into contact. To ensure that gas and glycol mixing will be continuous throughout the packing and the glycol will not channel, a well-designed glycol distribution header is installed above the packing. Contactors being designed today may contain structured packing. Now, structured packing is a group of corrugated metal sheets welded into a specific pattern and placed on edge in the contactor. Glycol coats these sheets and the gas flows between them. This type of packing is more efficient than bubble caps or random packing. Structured packing is used in columns from 6 inches in diameter up to 10 feet in diameter. Before the lean glycol enters the contactor, 2 things happen. The glycol is pumped up to the contactor pressure, and the glycol temperature is lowered to within 10 to 15 degrees of the inlet gas temperature. Now remember, it's best to have the glycol enter the contactor 10 to 15 degrees warmer than the inlet gas to eliminate condensation of hydrocarbon vapors. The lean glycol passes through a heat exchanger where it is cooled by the dry gas leaving the contactor. The glycol gas heat exchanger is sized to give the correct glycol temperature and usually does not require attention. Glycol entering the contactor at incorrect temperatures indicates an imbalance in the glycol to gas flow rate, a fouling problem in the heat exchanger, or that the reboiler temperature is out of adjustment. Above the top tray, a mist eliminator in the top of the contactor will remove any entrained glycol particles in the gas stream that have not settled out. This prevents liquid glycol from being carried out of the contactor and into the gas discharge line, commonly referred to as carryover. Carryover occurs when glycol contamination causes foam buildup. Carryover also happens when the gas rate is high enough to agitate the liquid on the top tray so that a foam forms that is too thick for the mist eliminator to handle. The gas rate must be reduced to eliminate carryover. Glycol level control on the contactor is important in stabilizing unit operation. The level controller should be adjusted to hold a uniform flow rate of glycol out of the contactor. It is more important to hold a constant flow of glycol out and let the glycol level in the contactor vary a few inches than to hold a constant level in the contactor and let the flow out fluctuate. Flow rate surges leaving the contactor will cause the reboiler to operate inefficiently and may overload it. The gas condensate glycol separator, also known as the flash tank or glycol gas separator, recovers gas and liquid hydrocarbons carried out of the contactor by the glycol solution. The gas leaves the top of the vessel and is vented, or may be used to supplement the fuel gas required for the reboiler. A pressure control valve maintains a back pressure on the vessel, usually 50 to 85 psig. Any excess gas is discharged through this back pressure valve. Separating liquid hydrocarbons from glycol before they enter the reboiler provides several benefits. It reduces the load on the carbon filter. It prevents carbon from building up on the reboiler fire tube. And it prevents glycol contamination in the still column, which can result in flooding, glycol loss, and possible damage to the column. Two-level control systems are typically installed on gas condensate glycol separators. The upper system regulates the flow of liquid hydrocarbons discharged from the vessel. The lower system regulates the flow of glycol from the vessel. Filters are installed in the glycol stream to remove solids and other contaminants which may cause plugging and foaming. There are two types of filters commonly used in gas dehydration systems. One type is used for solids removal, and the other for dissolved contaminants removal. For solids removal, fine screens, sock type, or cartridge filters are used. Now, solid particles cause erosion of pump pistons, valve seals, and discs, plugging of equipment, and foaming. Sock filters are the most commonly used type of solids removal. Sock filters contain cylindrical elements that are replaced as they become coated with solids. A differential pressure gauge measures the pressure drop across the elements. A pressure drop of 3 to 6 psig is normal as glycol flows through the elements. The pressure drop increases as the elements remove solid material and eventually become plugged. When the pressure differential becomes 15 to 20 psig, the elements should be replaced to prevent stoppage of the glycol flow and possible collapse of the elements. For removal of dissolved contaminants, activated carbon filters are used. When the glycol contains measurable quantities of light hydrocarbons, the carbon filter must be changed or reactivated frequently. Most glycol systems cannot be operated successfully without carbon absorption. Now, there are two types of activated carbon filters. Small systems like this one use a carbon canister with replaceable cartridges. Larger systems use a loose-fill carbon vessel that use granular activated carbon. When the loose-fill vessel is used, carbon particles, sometimes called fines, must be trapped to keep them from entering the glycol dehydration unit. This is especially important when a fresh carbon bed is put into service. Anytime the level of contaminants in the glycol increases, the carbon filter should be replaced. Monthly tests should be run to determine contamination level. The regenerator is a combination of the glycol reboiler and the still column. They work together to regenerate the rich glycol, making it lean again and ready to use in the contactor column. The reboiler supplies heat to separate glycol and water by simple distillation. Glycol is heated to a temperature between 380 degrees and 400 degrees Fahrenheit to remove enough water vapor to regenerate the glycol to 98.5 to 99%. The temperature of the triethylene glycol should not exceed 400 degrees Fahrenheit because TEG will begin to break down at higher temperatures. Reboilers can be direct-fired or heated by steam or hot oil. The direct-fired type, containing a removable firebox and fire tube, is normally used. An overflow weir maintains the glycol level in the reboiler. Excess glycol spills over the weir and flows downward into the surge tank by gravity. When the glycol level is low in the surge tank, fresh glycol is added to the reboiler, so it can be dried before going into the surge tank. This still column, or stripper, located just above the reboiler, is where the actual distillation of water from the glycol takes place. Still columns are normally packed columns and have fin condensers or reflux coils in the top. These condensers, or reflux coils, cool water vapor leaving the column and recover entrained glycol. The amount of glycol lost with the water vapor leaving the still column is controlled by the temperature of the water vapor. Now this temperature, called the still overhead temperature, should be set at the boiling point of pure water. Normally the pressure will be atmospheric, 14.7 psia at sea level, and the temperature will be 212 degrees Fahrenheit. Systems operating above sea level will require lower temperatures due to lower pressures. Systems with back pressure will require higher temperatures. If the still overhead temperature is above the boiling point of pure water, glycol carryover is the result, and losses will be higher than normal. If the still overhead temperature is below the boiling point of pure water, too much water will be condensed back into the glycol. This will cause both the reboiler heat requirements and fuel usage to increase. When the glycol flow rate exceeds maximum design limits, a condition known as column flooding occurs. Column flooding is when the still column fills with liquids. This occurs when the glycol being fed to the still column has a high concentration of light hydrocarbons. These hydrocarbons distill out of the glycol and condense in the upper portion of the column. Column flooding does not allow proper glycol and water separation. Rich glycol can be lost through the vent line when the column floods. Now the surge tank stores regenerated glycol for pump suction, and it is commonly positioned under the reboiler. Vapors, which are trapped in the surge tank, could cause a circulation pump to vapor lock. Therefore, a vent line is provided to remove these vapors from the surge tank. Most small dehydration units use a fluid-driven pump, while larger units generally use electrical-driven reciprocating pumps. In either case, the pump is a critical part of the unit because it has the only moving parts in the system. Now, before the rich glycol enters the pump, it passes through a strainer to remove large particles. Leaks can be a problem around glycol circulation pumps. Proper packing gland maintenance and the use of the manufacturer's recommended packing can minimize this problem. There are two types of heat exchangers used to cool the glycol in a glycol dehydration unit. Glycol to glycol heat exchangers, like these, and a glycol to gas heat exchanger. Now, lean glycol leaving the surge tank must be cooled prior to entering the contactor. The cooling allows the lean glycol to absorb the maximum quantity of water from the gas in the contactor. The heat exchangers are very important in the overall operating efficiency of the dehydration unit. They substantially reduce the amount of heat required by the reboiler and allow a maximum gas drying in the contactor. The first stage of glycol cooling occurs in the glycol to glycol heat exchangers. These two heat exchangers cool the lean glycol coming from the surge tank at 400 degrees Fahrenheit to a temperature of 212 degrees Fahrenheit. The final stage of lean glycol cooling occurs in the glycol to gas heat exchanger. Dry gas leaving the contactor passes through the glycol to gas heat exchanger, where it cools the incoming lean glycol to a temperature about 10 to 15 degrees Fahrenheit, above that of the natural gas entering the contactor. On small dehydration units, this exchanger is often a double pipe heat exchanger, which is literally a pipe within a pipe. Lean glycol in the outer pipe flows around outlet gas in the inner pipe. Larger units may utilize a shell and tube type of heat exchanger. Taking the temperatures of glycol before and after passage through the heat exchanger tells you what condition the exchanger surfaces are in. As the exchanger surfaces become more severely fouled, the temperature differential across the heat exchanger decreases. meaning that the exchanger isn't as efficient as before. When this occurs, you will need more gas to fire the reboiler. That wraps up the second section. In it, you saw the individual components that make up the glycol dehydration unit, how the components work together, and how the components work together to dehydrate natural gas and to regenerate rich glycol. All right, take some time now to read over this section in your student manual. Review this videotape if needed. Then when you're ready, answer the questions at the end of this section. Now in the next section, we'll see the importance of glycol conditioning and ways to reduce glycol losses. See you shortly. I hope you have a good understanding of how each component functions in a glycol dehydration unit. Now let's look at glycol conditioning and how glycol losses can be reduced. This is the third section of a three-section module on glycol dehydration unit operation. In this section, we'll examine the importance of glycol conditioning, operational procedures, and potential problem areas within the system. Various temperature and pressure conditions affect how efficiently the glycol dehydration unit can operate. First, let's look at operating temperatures in the contactor, reboiler, and still overhead. Then we'll look at operating pressures. In the contactor, the temperatures of the inlet gas and the glycol affect the amount of water removal from the saturated gas. Now, if you recall, at constant pressure, natural gas can hold more water as the temperature of the gas increases. And what does that mean? Well, it means if we keep the inlet gas temperature low, the unit will have less water to remove from the gas. Now, you also want to keep that lean glycol temperature down to a minimum when entering the contactor, but still 10 to 15 degrees Fahrenheit higher than the inlet gas. Why? Well, for several reasons. 1. Warm glycol absorbs water more easily than hot glycol. Secondly, we're trying to keep the temperature of the gas cool, so the incoming gas has less water in it. And thirdly, this helps to prevent hydrocarbon condensation. Now, the reboiler temperature is important because it controls the concentration of water in lean glycol. At constant pressure, higher reboiler temperatures result in greater glycol purity. The temperature range for TEG should be set at 380 degrees to 400 degrees Fahrenheit. Why? Because we want the range higher than the temperature where water boils, 212 degrees Fahrenheit, so that the water can be removed quickly, but lower than the temperature where glycol degradation begins, 404 degrees Fahrenheit. Remember what the still column does. It removes water from rich glycol, and it recaptures glycol trying to leave with water vapor. The temperature range we want to set for the still overhead temperature is between where water boils and where glycol boils. It's easy, because water boils at 212 degrees Fahrenheit, and triethylene glycol boils at 546 degrees Fahrenheit. Recommended range for the still overhead temperature is 212 degrees to 215 degrees Fahrenheit at sea level. Low still overhead temperature can cause reboiler overload and excessive fuel consumption. High still overhead temperature can cause glycol loss due to vaporization. Now let's look at operating pressures in the contactor, regenerator, filters, and GCG separator. If you operate the contactor below the proper design pressure, you will have problems. First, at constant temperature, water content of inlet gas increases as pressure decreases, causing the unit to work harder to dry the gas. Secondly, at constant gas rates, the gas velocity through the contactor increases as the pressure is decreased, causing carryover problems. Regenerator pressure will build up if there's a plugging or flooding problem in the still packing. An increase in regenerator pressure prevents some water from boiling out of the glycol, requiring higher temperatures in the reboiler. This wastes fuel gas and can lead to glycol degradation. As far as your filter goes, a pressure drop of 3 to 6 psig is normal as glycol flows through the elements. The pressure differential increases as the elements become plugged. Replace the filter elements when this differential increases to 15 to 20 psig. Operating pressure in the gas condensate glycol separator is 50 to 85 psig. Back pressure is maintained by a pressure-controlled regulator. Okay, now that you understand the various temperature and pressure interrelationships, you should be able to prevent costly operating problems such as high glycol losses, foaming, and corrosion. To really operate efficiently, you've got to minimize your glycol losses. Losses occur due to vaporization, entrainment, and mechanical leaks. Typical conditions which affect glycol losses include carryover with outlet gas leaving the contactor, leaks at the pump and pipe fittings, high still overhead temperature, the contactor column operating at excessive gas rates, foaming, and rapid changes in the gas rate. But how do you know if you're operating efficiently or not? Well, you take glycol samples in the field, have a laboratory test them, interpret the results, then you make the necessary adjustments to reach maximum drying efficiency. Now you can find out a lot by analyzing the glycol. Now it can tell you glycol weight percentage, water content, hydrocarbon content, salt content, solids content, pH of the glycol, iron content, and foaming tendencies. Let's look at a lab analysis from a typical glycol dehydration unit and see how efficiently we're operating. The glycol weight percentage refers to the amount of glycol in the glycol solution, also known as glycol purity. Lean glycol should contain about 98.5 to 99.9% glycol. Rich glycol content varies from about 93 to 96% glycol. Well, looks like our rich glycol sample is in the acceptable range, but the lean glycol is outside the acceptable range. This means there may need to be some adjustments made. Water content refers to the amount of water in the glycol solution. Low water content in lean glycol is vital to good dehydration. The water content in lean glycol should not exceed 1.5%. If the water content exceeds 1.5%, then the reboiler temperature is too low and or a heater is not working properly. The water content in rich glycol should not be more than 5 or 6%. Let's take a look at our sample. The water content for the rich glycol is acceptable. However, the lean glycol water content is too high. Again, this means that some adjustments may need to be made. Water content spread refers to the difference in water content between lean and rich glycol. A spread which is too narrow, 0.5 to 2%, usually means the glycol circulation rate is too high. The rate should be lowered to save energy, minimize glycol losses, and improve dehydration. A spread over 4 to 6% is too wide, and usually means the glycol circulation rate is too low and should be increased. The water content spread between our samples, approximately 3%, falls in the acceptable range. A good guideline for circulation rate is, for every pound of water to be removed, use 3 gallons of glycol. Hydrocarbon content refers to the amount of oil, paraffin, or condensate in the glycol. Keep it below 0.1%. Otherwise, problems such as foaming, plugging, or fouling will cause glycol loss and poor dehydration of the gas. The hydrocarbon content in our samples is below the range. Hydrocarbons get into the glycol in two ways: by condensing in the contactor when the glycol is colder than the incoming gas, and by carryover of hydrocarbon contaminants from the inlet separator or gas stream if the unit has no separator. Salt content refers to the amount of salt or chloride in the glycol. It should be kept below 0.01% by weight, or 100 parts per million. Problems occur when the salt content reaches almost 0.1% by weight, or 1,000 parts per million. These problems include a buildup of salt on the reboiler fire tube, resulting in decreased heat transfer efficiency, corrosion, which will eventually decay the fire tube, and hot spots on the fire tube, resulting in thermal decomposition of glycol and holes in the fire tube. Although the salt content of our samples is a little high, it is still in an acceptable range. Salt usually travels in the gas stream in a fine mist. Now, if the gas stream contains excessive salt, a coalescing or filter-type separator can be used to remove salt from the gas upstream of the dehydration unit. Solids content refers to the amount of suspended solids in the glycol. Suspended solids should be kept below 0.01% by weight using filtration. High solids content in glycol cause the following problems: increased pump wear from abrasion, accelerated corrosion and erosion, increased fouling of the fire tube, increased glycol loss due to foaming, and increased plugging problems. The solids content of our sample seems to be in the acceptable range. pH refers to the corrosiveness of glycol. pH is a term used to express acidity or alkalinity. It is based on a 0 to 14 scale. 0 to 6.9 is acidic, 7 is neutral, and 7.1 to 14 is alkaline. A pH of about 7.3 is considered a safe operating level. As glycol pH decreases, the equipment corrosion rate increases rapidly, and troublesome corrosive compounds result. Raising the pH above 8 to 8.5 is not desirable because a more alkaline glycol solution tends to foam and emulsify easily. In our sample, the pH of the lean glycol is acceptable at 7.4, but the pH of the rich glycol is too acidic. Check the pH of the glycol periodically and keep it on the alkaline side by neutralizing the acid compounds with alkaline chemicals. Iron content refers to the amount of corrosion products in the system. Rust is the most common. Corrosion products either come in with the incoming gas or they are the result of a corroding glycol system. If the iron content exceeds 10 to 15 parts per million, then corrosion prevention methods should be considered. The iron content of the rich glycol at 5 parts per million and lean glycol at 4 parts per million is acceptable. Foaming refers to the foaming tendency of glycol caused by contaminants. These contaminants in the glycol enter the system as gas entrainment. Water and glycol alone will not cause significant foaming. However, the combination of water, glycol, and oil does create excessive foaming. The main problems associated with foaming are improper gas dehydration, excessive glycol losses when the glycol foams out of the contactor, and additional equipment problems downstream of the contactor from glycol carryover. Foaming problems can temporarily be corrected by anti-foam additives, which cause the foam to break. The cause of the problem should then be identified and corrected. Improper use of anti-foam additives can increase foaming problems. The best preventative measure against foaming is the installation of a properly designed inlet gas separator and glycol filtration system. Good glycol filter maintenance and pH control are also very important. Well, that concludes the third section. In this final section, you saw how important temperature and pressure conditions can be, how to reduce glycol losses, and how glycol tests can pinpoint problem areas. Now read over the last section in your student manual. Review this videotape if needed. Then when you're ready, answer the questions at the end of the section. During this program on glycol dehydration unit operation, you've had the opportunity to review principles of glycol dehydration, to examine the system components, and to see how to properly operate a unit. Now, if you require additional information, there is an appendix at the end of the third section in your student manual, which includes a troubleshooting guide, a safe lighting procedure for a gas-fired glycol dehydration unit, recommended startup and shutdown procedures, and a chart showing water vapor content of saturated natural gas. A glycol dehydration unit uses several processes to separate water, hydrocarbons, and other impurities from natural gas. By properly maintaining your equipment and knowing what problems to look for, you can make the difference in successful natural gas processing. By understanding the various components in your glycol dehydration unit, and by knowing how to make the necessary adjustments, you can dry natural gas to the desired level and reduce your glycol losses while operating efficiently, cost-effectively, and most of all, safely.